Assalamualaikum. In this video, we will be sharing about the application of definite integral in volumes. In this application, we will be divided it into two parts, which is cylindrical shells and slicing. In slicing, we have two methods, which is Dick's method and Walsh's method. Okay, now volume by slicing. Volume by slicing is to divide a solid into thin slabs and then we approximate the volume of each solid. After that, we add all the approximation to form a Riemann sum, and lastly, we take the limit of the Riemann sum to produce an integral for the volume. What makes slicing method works? It is the fact that thin slab has a cross section that does not vary much in size and shape, which make its volume easy to approximate. Right after this, my friend will be sharing about the Dick's method in slicing.
Okay, first we're gonna show you on how to calculate volumes of solid revolution by this perpendicular to x-axis. Based on this region, there is a curve with continuous function, and R is the region rotating at x-axis with x-coordinate of A and x-coordinate of B. This problem can be solved by slicing. There is a cross-section of solid taken perpendicular to x-axis is a circular disc with radius function of x. So the area of the region is pi function squared. Thus, the volume is limit of integration from A to B pi function squared. For example, find the volume of solid under the curve y equal to square root of x over interval 1 to 4 revolve at the x-axis. First, we need to write the formula of volume. Volume equal to limit of integration from A to B pi function square. Then substitute all of the value. Volume equal to limit of integration from 1 to 4 pi square root of x square. Then it will become pi x. The antiderivative of x is x squared over 2. Then equal to pi x squared over 2. Then substitute the value 4 and 1. Become pi 4 squared over 2 minus 1 pi 1 square over 2 equal to 16 pi over 2 minus pi over 2. Simplify the value, become 8 pi minus pi over 2 equal to 16 over 2 pi. Next is the volume of solid revolution by this perpendicular to y-axis. There is a curve with continuous function and R is the region rotating at y-axis with y-coordinate of C and y-coordinate of D. So, the area of the region is pi function squared. Thus, the volume is limit of integration from C to D pi function squared. For example, find the volume of solid enclosed by y equal to square root of x, y equal to 2 and x equal to 0 revolve at the y-axis. First, we need to write the formula of volume equal to limit of integration from C to D pi function squared. As you can see, we want to integrate respect to y. Thus, everything must be in terms of y. So, we need to express x in terms of y. Y equal to square root of x, then x equal to y squared. Then substitute the value. Volume equal to limit of integration from 0 to 2 pi y squared. Then it will become pi y to the power of 4. Then the antiderivative of y to the power of 4 is pi y power of 5 over 5. Substitute the value 2 and 0. It will become pi 2 to the power of 5 over 5 minus 0 equal to 32 over 5 pi.
Now we will be moving on to the other method of slicing, which is the washer method. This method is for problem in which the generated solid revolution has a hollow region or a hole. The reason why it's called the washer method is because the cross section of the solid itself looks like a washer, like this. As you can see, when the region is rotated, you will have a colored region, which if we look from the side, yes, it really looks like a washer there. Okay, now let's move on to the solid revolving around the x-axis. Generally, we will use this function, and the a and b here refers to the limit of the function, while the fx refers to the further function from the revolving axis, or you can probably say as the one that has bigger volume, while the gx on the other hand refers to the function nearer to the revolving axis, or the one that creates the hole in the generated solid. For example, find the volume of the solid generated when the region between the graphs of the equation fx equals to 1 over 2 plus x squared and gx equals to x over the interval 0 and 2 is revolved around about the axis. So, first thing we have to do is to sketch a graph. Why? Because we need a visual to see the question clearly, like this. Okay, and then label it out and put all the variables into the function that we have seen earlier, which is this. try to simplify it as much as possible if you can, if it's possible, and because they are still within the same limit, so you can actually open up fx and the gx and then combine them before you integrate them. After that, you integrate the function as usual, and there you have it. The volume generated is equals to 69 pi over 10. Moving on to the y-axis. As for the solid revolving around the y-axis, it's similar to the way we did for those revolving about the x-axis. We just have an extra word, which is to change the terms of the function into y instead of x if it is necessary to do so. Then we can write it back into the general function that we shown earlier, but instead it's in terms of y. In this case, we can see that the function w is the bigger one, while the v function is for the one with a hollow region. What about the case where the revolving axis is not x equals to 0 nor y equals to 0? In this case, we have to get the area of the enclosed region first before we rotate that area to get the volume. Let's look at this example. Find the volume of the solid generated when the region under curve y equals to x squared over the interval 0, 2 is rotated about the line y equals to -1. Okay, first we begin again by making a simple sketch. Something that looks like this. Then we'll find the area first. If you look at the diagram here, you can see that it appears as if the x-axis is the function of the generated hole when y equals to -1 is the revolving axis. So when we find the area, we need to add 1 into the function, putting the function 1 value higher than the revolving axis. Our fx could then become x squared plus 1, and our gx will become 1. Simplify it and you will get the area function, which is Rx equals to x to the power of 4 plus 2x squared. Now that we have found the area function, we can now find the volume. How to do so? We will rotate the area in the given interval, which is 2 and 0. So put all this into the function, integrate it, and then we'll get the volume equals to 176 pi over 15.
Next is volumes by cylindrical shell. We use a cylindrical shell method when the cross-sectional area cannot be found or integration is too difficult. We must note that a cylindrical shell is a solid enclosed by two concentric right circular cylinders. The volumes of cylindrical shell with inner radius R1, outer radius R2, and height can be written as, which is 2 pi times shell radius times shell height. Now, let's take a look for the example. The function we're gonna use given by the question is y equals to square root of x, and also given the line x equals to 1 and x equals to 4. Okay, the first thing we need to do is we sketch the region. After we sketch, we're gonna have the region here between the line y equals to square root of x and the line x equals to 1 and x equals to 4. Now, to find the volume using cylindrical shell method, we use the formula v equals to integration of a to b 2 pi x fx dx. So x in this formula is a shell radius and fx is a shell height. Okay. Now the limit of integration is 1 to 4 2 pi. X is a share radius between the limit, which is rotating about the y-axis. So the share radius in this case, it will simply be x. And our shell height is gonna be our function, which is square root of x. I'm gonna write it as x the power of 1 over 2. Then we factor 2 pi out front of integration. This will be x the power of 3 over 2. Then when you have to integrate that, just use the power rule. 2 pi, it will be x power of 5 over 2 over 5 over 2. Then we simplify this, we will get 2 pi 2 over 5 x to the power of 5 over 2. Next, we just plug in 4 into this, we get 2 pi 2 over 5 for the power of 5 over 2 minus, we plug in 1 into this, 2 over 5 1 the power of 5 over 2. Then we will get 64 over 5 minus 2 over 5. We get 2 pi, we minus 62 over 5, and our final answer, we get 124 pi over 5. In this question, it said that the region R under y equals to x squared over the interval 0, 2. So this will be our region, and it's revolve the line y equals to -1. So we're gonna rotate this region at line y -1. So I'm gonna use this formula, just same formula from the previous example. So we need to find the shell radius and shell height. First, I draw a little shell in my region. It can be anywhere between the limit 0 to 4. I'm gonna suppose here as distance of y, well, the distance from the shell to the line I'm rotating about, I'm gonna consider as a shell radius. Just to remember, we always make our shell parallel to the line we are rotating about. So distance from the shell to the x-axis is simply by, and to find the shell radius, how many more we have to add to get to this line y equals to -1. So I guess this, we will add 1 to get a shell radius. Now our shell radius will be y plus 1. Now the shell height, if think about finding area between the curve, we just take top curve minus the bottom curve, so the shell height will be 2 minus square root of y. How I get square root of y? We make this x as a subject and we get square root of y. We factor 2 pi out front of integration 0, 4. Our shell radius is y plus 1. Shell height is 2 minus square root of y. And we integrate the rest back to y. So 2 pi, we get 2y minus y, the power of 3 over 2 plus 2 minus square root of y, and 2 pi, we integrate, just use normal power rule. It will be 2y square over 2 minus y power of 5 over 2 over 5 over 2 plus 2y minus y power of 3 over 2 over 3 over 2. We simplify this and we get y square minus 2 over 5 y power of 5 over 2 plus 2y minus 2 over 3 y power of 3 over 2. Next, we just plug in 4 to this and we get 2 pi whole square minus 2 over 5 4 power of 5 over 2 plus 2 4 minus 2 over 3 4 power of 3 over 2. And if we plug in 0, we will get 0. Then we solve, we will get 58 over 15, and our final answer will be 176 pi over 15.
In conclusion, we can summarize that the disc method is only used when the solid has a solid interior, while the washer method is only used when the solid has a channels that create interior surfaces or the solid is hollow. And the last method is the cylindrical shell method that is only used when the cross-sectional area cannot be found or the integration is too difficult. And that's all for pairs. We hope that this video can increase your understanding in the application of definite integral in volumes.